first, are there any questions about anything? I guess the important thing to have questions about is the midterm. Again, just to go over pretty much the same slides that I had last time. The midterm will be on Thursday. It'll be at 9:30, okay, usual class time. But make sure you know what location you're in. If you have a low ID number, below 116, okay, you go to Fry Hall 309, okay? If it's above 116 or above, you take it here, okay? Any questions about where people take the exam? Okay, that's important. And again, what do I say? I say that the best way to study is to look at the homework problems in the back of the book. I posted an exam, okay, so you can get an idea of what I put on an exam at some point in the past, okay, and from that exam, I think about the first 6 problems were fair game for you, okay, but otherwise were for later in the material. You're not allowed books, you're not allowed calculators, you're not allowed notes. I recommend you bring a pencil, okay, and a pen, these kind of things. The answers, problems I'm generally like to see, I want them to have some kind of quantitative or at least qualitative reasoning and clear answer. That's kind of my hope. Not, sometimes they're mushy essay questions. I try to avoid those, but maybe not completely. Okay? Any questions about the exam? Yes?
So do you need to cover anything which are in the slide but not covered in the class?
Okay, I would say anything that there is, in general, I have covered all, as far as I can tell, I have covered all slides except for when I said the background material for the homework, okay? And I had a bunch of slides that were more relevant on NLP to the homework. That stuff we're not covering, okay? Otherwise, I think I've covered all the slides. And, stuff from the slides or the book readings are fair game. But there should be large overlaps between those. Okay? Any other questions about the exam? Again, if you have any possible exam questions, a couple students have sent me some. Okay, feel free to send me questions to put on the exam. I will feel free to put them on or not put them on as I feel best. Okay? The one addition I have made since last time that I want to just culturate the students to. During the exam, you're going to be sitting here, you're going to get a paper, and there is going to be a question there that you think is badly written and that you don't know what, and you want clarification, and you're going to raise your hand, and the TAs are going to go, no, no, no. Okay? We're not going to... the TA is not going to answer, TAs are being programmed to not answer any questions about the exam, okay? This is to make sure that everybody gets consistent information, right? Okay? They're going to be in 2 different rooms. Would you like it if in one of the rooms the TAs start giving the answers to everything and in the other room they don't? That would be bad. So the rules are going to be that TAs are not going to answer any questions. If there's something you're uncertain about, write down your assumption, okay, on the paper, and then we'll see whether it's a reasonable assumption. But that's how you should communicate your uncertainty. Any questions about that? Okay. Any other questions about the exam? Okay. Going once, twice. Good. Okay, what I'd like to talk about today, I'd like us to move into a sort of a mini unit on statistics. And in particular today we'll talk about statistical distributions. And historically, if you said what is a data scientist, this definition was kind of what I liked. Was someone who knew more statistics than a computer scientist and more computer science than a statistician. Of course, distinctions get blurred, but it's important to know something about statistics. Okay, statisticians have been thinking about data for a longer time in some sense than computer scientists have. And they see the world through, a somewhat different lens than is naturally the case for computer scientists. And if you said historically what a statistician did, a statistician lived in a world where they kind of assumed there was a real population out there that you wanted to study. Okay, you couldn't talk to the entire population. Okay, so you did something like random sampling. Okay, to get a sample from that population. Okay, and properly doing random sampling was a probability, involves probability. When you add a sample, there were two different things you might want to do with it. One, you might want to compute descriptive statistics about it. What are the properties of this sample? How do you, this is where I put visualization and means and standard deviations and things like that. Also, you then would want to use this to try to make some inference about what the properties of the population really were. Today, if we think about a classic statistics problem, you obviously have polling going on. We have a presidential race. Everybody wants to know how it's going to end. Okay? There is a huge population. What do people do? They sample a small number of people, and they ask them who they're going to vote for. They analyze that into, to get some measured descriptions of the sample. They then try to reflect those statistics back to the whole population to get an idea of what they can infer about the behavior of the population. That's how statisticians lived. Any questions? Now, when they talk about inference, okay, one thing that comes on it that's kind of an important assumption in the statistical world is that when they see a distribution of a random variables distribution, okay, they have noticed that there are several important distributions that come up over and over again in practice, okay, and that have nice theories about them, okay. So it is useful to know what, these distributions, many of which I'm pretty sure you've seen in a statistics class before. But it's important to kind of have an intuition about what these distributions are, to have a sense when they arise, and to use them to think about it and such and such. So today's class, we're going to go through 4 different probability distributions, why they come up, okay, so you get, what they look like, why do they come up, and, what they're good for. Now, why do we care about classical distributions? You can put a name on it. It's not immediately obvious this is necessary. It's like you guys now live in this world of, this generative AI stuff, okay? And when you ask why did it make a decision, what kind of math is the thing using to make a decision, these models don't really have math. They kind of learn from data. They're what they are. Okay? Now, why do we care about the kind of closed form classical distributions? Well, one, the closed form formulas are sometimes useful. Okay? The idea that there are statistical tests for specific distributions is useful, okay? The classical distributions are kind of classical because they arise a lot, okay? And having a name for something that arises a lot is important on it, okay? And so this is why I think it's important to be able to know what these distributions are and talk about them intelligently. Now, one principle you should know is just because data looks like it's in a bell-shaped curve doesn't mean that it's normal. Just because, things get rare when they're large doesn't mean it's a power law, okay? So in principle, just because your data has a particular shape doesn't mean it comes from that distribution. That's why they have special statistical tests to validate that. But it's still useful to know where the distributions come from, and does it make sense that your data comes from that. That, I think, is important. Okay? Any questions? So the first distribution that I'd like us to be familiar with is the binomial distribution. What is the situation? Suppose we have n identical independent trials where you have two possible outcomes. Okay, maybe like a coin that comes up heads or tails. That's kind of the standard one. The probability that we will get exactly x heads, if it comes up with a probability of a head of p and a tail of 1 minus p, the probability we will end up with exactly x heads out of n, okay, is we have to choose how many sequences of x heads and n minus x tails there are. That's n choose x. That counts the number of patterns of heads and tails with this count we can get. For each one of these, the probability of it occurring is whenever we want a head, we've got to get a head. The probability of getting a head p is p. The probability of getting a tail where we want is 1 minus p. This is the probability of any particular sequence with x heads, and that times the number of different sequences that have x heads gives us what the probability of ending up with exactly x heads are. Any questions about that? Now, we saw the binomial distribution earlier when we talked about the probability, what was going to be the batting distribution, the distribution of batting averages of a 300 hitter. Okay, if you get a hit with a probability of 0.3, make out with a probability of 0.7, what's the probability you're going to, if you're batting 300 and 500 at bats, that means you've got, I think it is 150 hits or something like that. Okay, this would give you what's the probability of that you're going to bat exactly 300 given you should be batting 300. Any questions about that? What does a binomial distribution look like? Okay, is it bell-shaped? Okay, the answer is usually classically looks bell-shaped. Okay, here we have a world where you say how many heads will you get if you flip 200 coins? I made a mistake here. This should be 200. Somebody remind me that by email and I'll change it. But if we flip 200 coins, this is showing me the distribution of the number of heads. According to the binomial distribution, this shows as a nice bell-shaped thing. Does everybody agree? I talked about another binomial distribution at one point. What happens if you have a light bulb? Again, light bulbs, as I usually think of them, are light bulbs. You screw them in a light socket, they go out occasionally. Okay? When I bought light bulbs, they would say they were good for 1,000 hours. You could imagine every hour there was a probability of 1 in 1,000 that the light bulb was going to blow. Okay? And that would be one way to get a light bulb with an expectation of 1,000 hours of service. If we ask, we have 1,000 light bulbs, and we're going to do, we're going to have 1,000 light bulbs, and there's a 1 in 1,000 chance every hour, it's going to burn out. How many burnouts do we see? Okay? If you look at this, this is going to be a binomial distribution too. Okay? Does everybody kind of get that idea? There was a 37% chance that you never got any bulb. If you the bulb never burnt out. In this case, an equal probability that one of them burnt out. Okay, if you got really unlucky, you might lose 4 or 5 bulbs in 1,000 trials. Why is this not bell-shaped? Okay. Binomial distribution is bell-shaped. Why isn't this bell-shaped? Is it bell-shaped? Okay. It's because, first of all, this distribution is always shifted to the left. You can't have -1 burnouts, okay, of a bulb in 1,000 trials. Does everybody see that? And if your probability of something happening is low enough relative to the number of trials, the distribution shifts to the left. Okay? And here we have something that looks more like a half bell-shaped curve. Right? Any questions about that? Yeah.
So, like you would say this is right skewed, this graph, right?
Would I say this is right skewed or left? I get left from right mixed up. So I'm not sure. I would say that it's shifted, and I wouldn't make a definitive view whether it shifted left or right. If someone needed to look it up, I would look it up on the internet if I needed to know left from right.
Just the question would be, if p is less than 0.5, then it'll have a shift in the direction of this graph, and if p were greater than 0.5, it would have the opposite shift.
Yes, that would be true. So if you had a loaded coin, which would come up heads more often than 0.5, the expected number of heads would shift in, this distribution would shift in that direction. Okay? And maybe change also the standard deviation. It's not just a shift, it would presumably get compacted. Suppose you had a really loaded coin, and the probability of it coming up heads was 1. What would that binomial distribution look like after you had 1,000 coin tosses? It would look like a delta function. Everything would be at 1,000. So if you change p, it's not just that the mean shifts, it's that it also gets squashed or expanded, right? Any questions about that? So why is it that it gets squashed or expanded? Squashed or expanded is a question about standard deviation, about variance. Okay? There is a closed form for the variance of a binomial distribution. Okay? The standard deviation is square root of n times the probability of heads times the probability of tails. Okay? If we think about it for a fair coin, that's going to be n times 1/2 times 1/2 square rooted. That's going to be 1/2 square root n. Does everybody agree with that? This is a useful fact to know. Okay? It tells you something about what the likelihood of being far from the mean is on a standard deviation, on a random walk. So let's say we were taking a walk where you're going to randomly choose to go either to the left or to the right at each step based on flipping a coin. I'm starting here. You're going to be flipping a coin and you're going to be telling me go to the left, go to the left, go to the right, go to the right, go to the left. How far from home should I expect to be after n steps? Does everybody see what the question is? Okay. How far from home should I expect to be, roughly? Somebody with a hands?
If n is even, you stay at home. If n is odd, so you stay either in left or right.
Okay. On expectation, if you say, what is my expected position after flipping n coins? My expected position is where I start. But that's not, but the question, if I now ask you, what is my expected distance from home? It is not going to be 0. Okay? Distance, remember, is a positive thing, right? You know, my distance to you is the same as your distance to me, right? How far should I have to travel? An expectation, how far away from home will I be? Okay, about. If you flip n coins. Okay? Any ideas? Yeah? It's something that's going to be something like the square root of n. Okay? This is kind of important. Okay? So, you know, when, you know, exactly what the constant is, we'd have to kind of work out, right? You know how you would compute it. You know how to, if you think about it, it's the number of ways n choose x. If x was n over 2, then you were home, right? If it was n over 2 minus 1, you were 1 position over, 2 positions over. You could write a summation to give you what this quantity would be. But the important thing, if you look at a distribution like this, if you know the standard deviation is about square root n, you're going to be, you know, big O, big theta, if you do your algorithms right, of square root n steps on average from where you are. Okay? This is kind of important to know. Any questions? What's the difference when you flip n coins? What is the difference? What is the probability of getting exactly the same number of heads as tails? Assume it's an even number of coins you're flipping. Okay? If you work it out, the probability of getting the same number of heads as tails is only 1 over square root n. So it's actually quite rare to get a perfect split. Usually you're going to get n over 2 heads plus or minus some small constant times square root n. And that gives you a way to think what the spread is on this distribution. Any questions about that? Okay, I find this is a fact that is useful to me sometimes. Any questions? Okay. The second distribution, which we're going to see is quite closely related to, the binomial distribution, is the normal distribution. What is the normal distribution about? This is the bell-shaped curve that everybody assumes. You see something bell-shaped, you always think that's a normal distribution. What is it that's distributed by the normal distribution? When people do studies of IQ, the IQ in the population looks like it's normally distributed. Height is normally distributed, okay? A lot of things in the world seem to be normally distributed. Okay, and why that is, we'll think about in a little bit. Does anybody know why things are normally distributed? Why is height normally distributed? I don't really know. I mean, I'll give you a theory a little later. Okay, maybe it'll make some sense. But to a certain extent, this is an observation. Okay, the normal distribution is a useful distribution, because it's a probability distribution that is completely parameterized by the mean of the distribution and the variance, or equivalently the standard deviation. For any set of points data, it's easy to compute the mean, it's easy to compute the standard deviation, and if you believe your data is normally distributed, then what's great about that is if you use this thing, you naturally get a complete probability distribution. And how accurate this probability distribution fits your data, depends upon how close your data really is to the normal distribution. Any questions about that? So what is a distribution? It's something that is exponential in the deviation from the mean. If you look at that, what does that say? X minus the mean means that the exponent is a function of how far you get away from the mean. And there's a negative sign there. What does that mean? That means that the further you get from the mean, the lower this value is going to be. It's going to decrease exponentially with your distance from the mean. That means that you're it's rare that you get, the probability of getting something very far from the mean is low. Okay? And this is, put into the proper perspective by the variance. Okay? Any questions about that? That's kind of where the normal distribution comes from. Okay? So what are the things that you really need to know about the normal distribution? One is, as we'll show, it's a generalization of the binomial distribution. Okay? And sometimes it's a binomial distribution when n goes to infinity, that kind of thing. With the binomial distribution, the parameters we had were n, the number of flips, and the probability of heads. The binomial distribution is also a two-parameter distribution, but it's in terms of mean and standard deviation, which is easily measured. One difference between the normal distribution and the binomial distribution is it really is bell-shaped. The normal distribution is a continuous distribution. You can have negative values. It goes infinitely in both directions. Okay? And the sum of independently normally distributed variables is normal. What does that mean? Suppose height is normally distributed, right? And suppose IQ is normally distributed. What do we know about people? If we represent people by the sum of their IQ and their height, is that normally distributed? The answer is yes, right? If x is drawn from a normal distribution and y is drawn from a normal distribution, the variable x plus y is also normally distributed. Okay? Any questions about it? Okay, good. Now, what is very, very useful about the normal distribution? It is, again, it's completely parameterized by the mean and standard deviation. Okay? Suppose we take a normally distributed variable, let's say like height, and convert height to z-scores. We know that the mean and mode and max, the mean and the mode and the median is going to be at 0. Things that people who were taller than average were going to have positive z-scores. People were going to have negative, less than average, were going to have negative z-scores. But what's interesting about a normal distribution is because height was normally distributed, z-scores of height are going to be normally distributed. They're just a linear transformation of those values. And if you look at this distribution, where you have mean, mean 0 and, standard deviation 1, we can interpret any point in terms of how many standard deviations it is from the mean. And the interesting thing is that those bounds are very well prescribed. 68% of all data is within one standard deviation of the mean, if it's normally distributed. What was that bound which we had? We had an inequality before. On all probability distributions, how much of the mass must lie within one standard deviation of the mean? What? 68%. 68% if it's normally distributed. What if I don't tell you it's normally? What if I tell you it's Skinner's distribution? How much mass of Skinner's distribution must lie within one standard deviation of the mean? I didn't tell you what Skinner's distribution was. But we did have a result in here where we did prove a bound on that, right? What was that? Markov's inequality. And what did that give us? It gave us that there exist distributions where none of the mass is within one standard deviation. Within two standard deviations, at least 75% has to be there. That's what I remember, right? So the normal distribution tells us that 68% has to be within one standard deviation, 95% must be within two standard deviations, and 99.7% must be within three standard deviations, okay? This tells us that, we now have ways of thinking about the distribution very precisely once we know that it's normal, okay? Any questions about that? What is the mean height, okay? The mean height in the world is something like, I'm used to thinking of it as, I think of it as 5'8", just because that's what I claim to be, right? What is the standard deviation of height? Does anybody have an idea? I want to say something like 8 inches or so. It's very, very rare to have somebody. How rare would it be if that was true, if this was 5'8"? Okay? And let's just think about it. If I'm making this up, that if the mean was 5 foot 8 inches, how much is 5 foot 8 inches in inches? 68. And if the standard deviation was 8 inches, okay, how rare would it be for someone to be 7 foot tall? Okay, is this something we can compute? Well, how many standard deviation? How tall is 7 feet? 7 times 12 is what? 84. Okay, 84 minus 68. How much is this? I haven't done this before, but let's see if it works out. 16. Okay, that says 2 standard deviations. If I'm right about these numbers, that says that it would be 2 standard deviations from there. What fraction of the world's population would be 7 foot tall if this was right? Well, it would say 2.5% of the world's population is there, is 7 foot tall or greater. Is 2.5% of the world's standard population that tall? So it doesn't work out. What is wrong in this calculation? Can anyone guess what's wrong? My standard deviation was too high. Does everybody see that? Okay. So let's try to do this again, maybe in a different way in the context of IQ. IQ, I do know, is normally distributed. The mean is 100, and the standard deviation is 15. Okay? If I ask you then, how many people have IQs above 130? Does everybody agree that the people with IQs in this case are the same as the people I said were 7 feet tall, right? 2%, 0.5%. Any questions about that? Okay, this I think you might believe. Okay, we agree my standard deviation was too high there. Any questions about that? What is the IQ of the smartest person in the world? Okay, if I have to now derive what the IQ of the smartest person in the world is, how would I do that? Okay, I could give everybody in the world a test and take the highest score. Okay? Is there anything else I could do to figure out the IQ of the smartest person in the world?
Find out a point where no one lies in the standard deviation from the mean.
So I need to know how many standard deviations from the mean is it until I've got basically one person sitting there. Does everybody get that idea? And what does this mean? Okay, how many people in the world are there? Okay, there are something like, when last I counted, I think of 8 billion, or am I behind the curve? I'm probably a little bit behind the curve. But let's say we have 8 billion people, okay? We know that it's 15 the standard deviation is 15, so every 15 I am getting smaller and smaller fractions of the world away. And when I did this calculation, it would say that the smartest person on Earth would have an IQ of about 200, which is about what you kind of see, or you read in the newspaper about. That's not a crazy number, okay? So what's exciting about the normal distribution? You know what it looks like, you know how to think about it. You can reason about things once you know that they're normally distributed. Any questions about it? This is what I find useful about the normal distribution. Any questions? Okay, good. Now, what's not normal? Okay? There are a lot of things in the world that are not normally distributed. Is the height of the people in this room normally distributed? Okay, I told you I've made glib comments about height being normally distributed. Is height in this room normally distributed? And I will say no, because for one thing, we have a mixture of men and women, which I'll say are roughly the same, in terms of count. But it is clear that on average, women are shorter than men. Okay? And if men are normally distributed and women are normally distributed by height, okay, then the union of them is going to be a lumpier thing. Does it look like a bell-shaped curve? This curve looks bell-shaped to me. If I had a small enough number of samples, would I believe that that's perfectly bell-shaped? You could convince me of it. But does everybody see that the mixtures of normal populations do not yield a normal population? The variable that is the sum of two different normal distributions, that would be normally distributed. But mixtures of populations are not normal. Does everybody see that? Okay. Now, do we think that men are normal? If we take a look at men's heights, are men's heights normally distributed? I see people nodding. And has anybody ever seen a kid before? Okay. When you have a 1-year-old, what's the height of a 1-year-old? Okay? Where are they going to be? They're going to be out here someplace, right? If you count them as men, okay, certainly the union of kids and adults, again, you've got a population mismatch, right? Are there other weird populations if we start talking just about men's heights? Are there other weird populations that we would have to consider to prevent it from being perfectly normal? Maybe there's people who've been amputated. Does everybody see if they lost their legs? There's some population of people. This is something that isn't the normal variation, right? You could imagine that there may be forms of dwarfism or something like this that are outside normal variation of things, okay? So whenever you see a statistical distribution, odds are it's not perfectly normal. It's often close enough to normal that it's worth thinking about it as normal, so you can use these bounds to reason about it. But understand that real data are often drawn from mixtures of populations. Next real class, not the midterm, but when I start lecturing again, I'm going to talk about statistical tests. Statistical tests can be used to rigorously prove, is the data normally distributed? But my conclusion is whenever you take data that you think is normally distributed and you run it through a rigorous statistical test, it always fails because there's always kind of some mixture of populations. That doesn't mean that it's not a useful thing to think about, but it's important to know, not think about it religiously. Any questions about normal distributions and mixtures of populations? Yes?
So aren't
Okay, the student t-distribution is something that arises from a test for how similar two samples are. We'll talk about the t-test next class, next real class, okay? And that's a distribution that kind of arises in trying to test whether two distributions are the same, not necessarily whether one is normal or not. But you could imagine, for example, one way to test whether something is normal. I'll give you a hint. You were mumbling about the t-test and stuff like that, the student t-distribution. You could imagine, how could I tell whether the heights of men in this room are normally distributed? I could take samples from the theoretical normal distribution and then compare that according to the t-statistic with the distribution of heights that I see in here. And either those distributions behave the same or close enough to the same that we would declare that both of them are the same, meaning both are normal. Or we would say they're probably not from the same distribution. I don't know if that helps you or not. Any questions? Okay, good. Now, where does the normal distribution come from? Okay, I think you guys can all believe that it's good to have a bell-shaped curve to think about. It's good that we know it kind of the properties and the distribution kind of matches what we see in terms of many variables. The place where the normal distribution came up is in basically trying, as a consequence of trying to prove the central limit theorem. What is the central limit theorem? It is an observation that if I have n independent samples from any distribution, okay, the mean, or equivalently the sum of those samples, okay, converge to a normal distribution. Okay, let's think what that means. Suppose we have a distribution that looks like this. Does everybody see this distribution up here where I'm moving my mouse? This distribution is a weird population distribution. It's a bunch of people that are below the mean, a bunch of people that are above the mean, and some weirdos kind of a little bit less than the mean. Does everybody see that? This is an arbitrary probability distribution. Suppose, let's say, in the slide below, I randomly sample 5 elements from here, and I average them, okay? And I keep doing this with random samples of 5, okay? What do I end up getting? I get a distribution that looks like this. Does everybody see that the average of, this is the top one you could think of as what do I get as the average when I make one sample, right? By the time I get 5 samples, what do I get? I start getting a curve that looks like it's bell-shaped. Does everybody kind of see that? The average value here is going to be the average value, the mean value of the distribution. But if you think about it, if I pick 5 elements, some of them are going to be bigger than the average one, some of them are going to be less than the average. This is going to end up yielding a smooth distribution. And as I get samples that are larger and larger, I take more and more samples. The value of the average is going to become more and more stable, meaning the standard deviation of this distribution is going to get smaller and smaller, right? So again, this was the case when I did 5 samples from here. This is when I took 25 samples from here and averaged them. What do we expect? That if we have a population distribution with a mean of mu and a standard deviation of sigma, when we have, look at the distribution after n samples, okay? The mean is still going to be mu, okay? And the standard deviation is going to be sigma over square root n. Where was that square root n come from? It's kind of like a random walk, the variance, you have this kind of thing, okay? Any questions about that? This is why the normal distribution has that very special property to it, that e to the minus some complicated thing divided by 1 over 2 sigma with square roots in it and stuff. It is because the normal distribution is the distribution of the mean of independent samples as n approaches infinity. Okay? Any questions about that? So this is kind of the important thing. This is why the the normal distribution is so important. Okay, and why it has that very specific closed form expression. Any questions about that? Okay. Now, I told you that the normal distribution, the binomial distribution, is a normal distribution. Why do we know that? Well, what is the binomial distribution? The binomial distribution represents the number of heads in n tosses. One way to think about that is that is the sum of n independent samples, where each sample is either 0 or 1, depending upon when you flip one coin, it comes back heads or tails. Does everybody kind of see that? Okay? So the reason you get, what is the distribution, the probability distribution of heads after one toss? There's, the probability of getting 0 was 1/2. The probability of 1 was 1/2. Right? If we now keep drawing samples from this, how many heads do we get? The distribution's going to get smaller and smaller and more normal, and eventually the expected number of heads is going to look something like that. Okay? Any questions? Or the average number of heads is going to look like that. Okay? Any questions? So, what do we know? The average number of heads is approximated by a normal distribution. Okay? Now, if you wanted to tell me, come up with a theory as to why people's heights are normally distributed, can anyone come up with a theory of this? And make up a world where your heights really are explained by the normal distribution, based on this kind of an argument. Yeah?
If you say that you're the average of the heights of your parents, and you're choosing two people to
Okay, so one possibility is say you're the average of your parents, okay? And that would mean that you are going to be the average. If your parents were randomly sampled from the population, that seems like a good hand-waving argument. I kind of like that. But why is it so normal? Well, maybe you might say you're also kind of the average of your 4 grandparents, right? Or the average of your 16, great-grandparents, right? So that's kind of a hand-waving argument that I kind of like. Does anyone have another one? That wasn't the one I was going to come up with, but I might like that one even better. Okay? Yeah? Okay, so another thing might be that it's a genetics thing. That, to a certain extent, what is true. Another argument might be that height is something that is governed by thousands of different genes, right? You're getting, typically, maybe you get there's two different alleles. And if you've got for this gene, the positive allele, you might be a millimeter taller than if you got the negative 1, right? Then what's your height going to be? It's going to be the sum of these independent samples, right? And that might give you a normal distribution. Okay? That's another argument, hand-waving argument that this could be true. I was going to think of it a little differently, which is that every day you have, let's say you grow, when do you stop growing? When you hit, let's say 18. That means you've got 18 times 365 days to get taller, right? What happens if you don't eat on some day? You don't get taller that day, right? You could imagine that every day your height is a sum of how much you grew every day. And if you grow every day a little more or a little less, depending upon whether the sun was shining or how much you ate, then that total would come out to be the sum of these things. Any questions about that? Okay? So those all might be arguments as to why height is normally distributed. But if you can come up with an argument for what you are doing, maybe this gives you a way to think about it. Any questions? Okay, good. Now, let's talk about any other questions about the normal distribution? Okay. Let's talk about what I will call lifespan distributions. Okay? Suppose on any given day you have a probability of the probability of surviving, living through the day is probability P. Okay? When do you die? If you have a coin that's flipping every day, cosmic day, God is flipping a coin and saying with probability day P you live, and with probability 1 minus P you die. When is it that you're going to die? Okay? If you're going to live a total of n days, what had to happen? Coin had to come up heads n minus 1 days, and then come up tails, right? How many times is it going to come up tails for you? 1 time, right? Okay? So this is a lifespan distribution where if we assume that the probability of you dying every day is the same, this gives you the probability of living exactly n days. Does everybody kind of agree with that? Okay. Now, at some point in here, I talked about the light bulb distribution. If I wanted to model how long light bulbs live, I could have said, well, a light bulb burns out every, with probability P. The binomial distribution counted how many light bulbs died out if I had 1,000 times turning it on and off. That's not the same thing as knowing what is the expected distribution. How many light bulbs live 1 day, 2 days, 3 days, 4 days? If I really wanted to model light bulbs, I claim that this kind of a distribution, okay, would be a better distribution. Does everybody kind of get that idea? This is giving me the lifespan distribution for any number of hours, okay? And the presumption is that if I sum that up as n goes from 0 to infinite, it will add up to 1. Any questions about that? Yes?
Just being sure, this is just another name for the geometric distribution?
Is this another name? I think, actually, no. I think this is another name for the, the Poisson distribution. I think of the geometric distribution as another name for the binomial distribution. Do people agree? Who here agrees with me based on what you know? I hear one person. Who here disagrees with me? It's okay to disagree with me.
Yeah, I thought this was geometric as well. When you first brought it on the slide, that's just how I had been called.
Okay, as I recall, okay, the geometric distribution was you had Bernoulli distribution. Okay, Bernoulli distribution is the same as the kind of binomial distribution, right? Okay, I don't use the word named geometric distribution, so that's why I didn't worry about it. Maybe this is, let's say I don't know, someone send me an email, I'll double check this for myself, okay? But I think clearly this is a lifespan distribution, and I understand it as a lifespan distribution, okay? Any questions about that? Now the lifespan distribution, okay, is, I claim, what you also get by the Poisson distribution. What is the Poisson distribution? The Poisson distribution measures the frequency of intervals between rare events. That's the way that we're doing. And what is the rare event in the lifespan distribution? It was, the rare event was you dying, right? Between you being born and you dying, right? So the Poisson distribution is something that is parameterized by only one thing. What is the probability of living exactly X, a period of X, the interval between the interval between rare events being X? It's a function that is the mean to the X, e to the minus mean, divided by X factorial. Now what is this? The Poisson distribution is a lifespan distribution. It's the distribution of gaps in some sense between events. It is parameterized not by, the first one was parameterized by this probability P, N and P, okay? For the, the Poisson distribution, it's parameterized by, X, which was the equivalent of, the length, the equivalent of N last time, and the mean gap, the mean life expectancy, okay? So instead of it, I think that the distribution we had on the previous slide made sense because it was a function of the probability. Probability of either, every time you're either going to die or not die. Okay? Another way to think, though, about the expectation is that if you think about an expected lifespan, the expected lifespan of a lifespan distribution is completely parameterized by that probability P. Okay? What is the expected lifespan of something? It's K times the probability of living exactly to K. Does everybody see that? This should be clear. The expected lifespan of, in any kind of a world, is, for all possible lifespans, what's that lifespan length times the probability of having exactly that lifespan length? That probability of having exactly the lifespan length by the previous model was completely a probability of P, the daily probability. So a distribution parameterized by mu is in some sense equivalent to a distribution parameterized by the daily value of P. Any questions about that? The other thing that turns out to be true is that the Poisson distribution of lifespans is in fact also a normal distribution, but one where the variance, where the standard deviation is the same as the mean. That's one reason how we get away with one parameter, just the mean, okay, instead of having the variance, okay? Any questions about that? So what is good about having a a distribution of lifespans? Again, what is the average age that what is your life expectancy? What is the average age that people live to these days? Does anyone have an idea? 80. 80 is a good one. We can argue hopefully it'll get bigger in your life, but we'll find out. Okay? But you could imagine then, if we had our Poisson distribution, given the fact that the life expectancy is 80, if lifespans were Poisson distributed, we would get a bell-shaped curve of how long people live, okay? And, you would see that people start dying around 55. This is where I am, so I'm starting to kick up a little bit, right? And people live to be about, it looks like according to this, non-trivial number of people live to be, about 105 or so, okay? Is this Poisson distribution a good model for life expectancy? Yes or no? Okay, it's not a terrible model. It's giving us numbers that are not impossible to believe. If we wanted to make it better, what is the questionable assumption in lifespan prediction if we're going to use the assumption of the Poisson distribution? Okay? If you took a look at this thing, let's go back to our original expression. The whole Poisson distribution was parameterized by the fact that we had a probability P of dying on any given day. And that this is presumably a global constant, right? Do we believe that's true with life expectancy in general of humans? What changes as you get older? Someone with a hand, yeah?
The probability of you dying increases.
Probability of me dying on a particular day increases as you get older. There is something called the Gompertz curve that governs this kind of thing. So the real observed frequency turns out to be something like this. That in fact, yes, we have a mean of 80, okay? But first of all, bad things sometimes happens to young people. You guys got to drive carefully, right? And, there is a bigger hump and a quicker decline than you would expect like this. And the reason is simply because the daily probabilities are not constant, okay? If you take a look at this thing, at your age, your probability of dying in the next year is, look at that, nothing, almost nothing. What's that, not 1%, 0.2%, right? You guys are pretty confident that you're going to make it to graduation, right? Now for me, it's already on a daily basis, okay? 10 times what you're up to, right? And this is an annual basis, okay? And by the time you get to be 100, it happens pretty quick, right? So this is why, let's say, life tables are not completely a Poisson distribution. But thinking about things in terms of the gaps between rare events, I think, is a good way to get explanations of things. Okay? Any questions? Now, in the United States, it was historically the case that the average family had 2.2 kids. If you wanted to say, what's the number of families that have 5 kids? Could you derive that from just knowing what the expectation is? You're saying no. If the way people had kids is every time they would have a kid, they either say, this was nice, or they say, forget it, I'm shutting down the factory. Okay? If they did that with a probability of P each time, you would have a Poisson distribution. And again, when I tried to fit this data, it actually fit pretty well in general. And not perfectly. But again, I think this gives you a way to reason about it. That's what I like. I like having a qualitative reason. Why is it that a distribution looks like a particular thing? Okay, it may not be perfect, but I think it's useful for reasoning about. Any questions? Any questions about the Poisson distribution? Okay. The last thing I want to talk about for today is power law distributions. Okay, and these we've probably mentioned a couple of times in here. Power law distributions are relatively new in the language of people thinking about distributions. Okay? You know, I could say that, you know, while I was a professor here was the famous paper that said, hey, power laws are important. Okay? What is a power law? A power law is a probability distribution where it says that the probability of a value x is going to be x to the minus a times some constant c for constants a, which is the exponent, and c is the normalization constant. What does this mean? Okay, if we interpret this thing saying, it says that as x gets larger and larger, yes, it gets rarer, okay, by a, you know, if we, you know, double x, we reduce the probability by something like 2 to the a. Okay? That's kind of the way to read this thing. The important thing in a power law is the a constant. The c constant you usually don't even try to fit. It's just there to make sure that when you sum up over all values x, the sum of these probabilities needs to go to 1, right? Well, for any value of a, there exists some c where that's going to be true. Okay, so that's what c means. What's interesting about power laws? Power laws don't cluster around a mean. They're not bell-shaped. Okay? They're not uniform. Okay? Okay? Power laws have the property that large values are rare, but they do occur. 13-foot people do not occur, right? Okay? But people who are as many standard deviations away, you know, as from the mean, you know, of certain things, mean wealth, do occur. Okay? That's kind of what makes power laws interesting. And power laws arise whenever something is unequally distributed. Okay? You say that you've probably heard a saying where 20% of the population gets 80% of the wealth for some value of 20 and some value of 80. If this kind of thing always holds, you get a power law. Okay? Any questions? So recognizing when there are power laws in the world is important to think about. Now, population size in cities is governed by power laws. Okay? Let's say we take a look at this is from a database of the 150 largest American cities that I took. The average city population for one of the top 150 cities is 165,000. The standard deviation among the cities on that list was 400,000. This should look a little bit ugly to you because the standard deviation is large relative to the mean, right? We liked our standard deviations to be like coin flips in normal. It was square root n, right? Instead, it looks like it was, the standard deviation was twice the mean. Okay? Still, if city population was normally distributed, if I had 100 cities, okay, and I knew the mean and the standard deviation, okay, 100 cities, that would mean a probability of about 1 in 100. That's 2 or 3 standard deviations from the mean. If you work through that, the largest city in the United States should be Indianapolis. Is Indianapolis the largest city in the country? How big is New York? New York has 8 million people in it. Okay? Does everybody see that this is kind of, this is far bigger than what you would expect by a normal distribution? Normal distributions do not capture the population of cities. Okay? There is something else going on. Why is it that New York City has 8 million people? Can anybody figure out? Why does New York City have so many people? Any explanations? Yeah? A lot of opportunities. Why are there a lot of opportunities? Is it because it's near a lot of mines and mineral resources and stuff like that? No. Okay. Finance. Why is it finance there? Yeah? Wall Street, why? You couldn't have built Wall Street someplace else? The people couldn't trade money in Chicago or something like that?
We were the nation's original capital. 100.
You're saying it's because the reason New York City has so many people is because it has so many people. That's the real reason, okay? You are attracted to New York City because of opportunities. And why are there opportunities? Because the opportunities are going where the people are. The people make more opportunities, right? You have enough people there, somebody's going to start a bank. Somebody's going to, do something to hire other people, right? Jobs are going to come here because this is where the employers are, right? And when they do, they'll bring more people. New York City is so large because the rich get richer, okay? And small cities are starving because why would you stay in a small city when there's so much more opportunity in the big city? Okay? Any questions? That is why power laws arise. The rich get richer. Any questions? So, how do you tell when you have a power law? You have a power law when, if you did what is this picture here? This is a picture of, I told you I had a database, I guess I had 300 cities in my data set, fine, okay? This is showing the x-axis is the city by rank, the y-axis is the population. Why is it decreasing? It's because I sorted the cities by population. Does everybody see that? Where is New York City on this data? What? Yeah? It's off the chart. Does everybody see that? It's got to be up, if this is 800, it's got to be 800 times 10 times, that's 2, 3. It's got to be up about here. At least I'm looking at the screen, right? So we don't even bother to plot that kind of thing. Now, on the other hand, if you plot it on a log-log scale, okay, where you take the log of the rank and the log of the population. When you do this, it magically tends to fall on a straight line. Does everybody see that? Again, I didn't draw the points, but kabunk, kabunk, kabunks, the city can now appear, the log of the city population can appear on here. Okay? And this regular relationship is a consequence of the fact that, when you double the value, okay, when you double your x position, your y position is going to be proportional to that move, right? That's because the probability of it becoming rarer was by, 2 to the alpha, okay? It was going to be that would define this regular kind of a linear decay. There's a reason, if it was power law distributed, it has to be a straight line on a log-log plot. Okay? And that's what's being shown here.
When you say log-log plot, you mean like the x-axis log scale and the y-axis?
X-axis is log scale and the y-axis is log scale.
But not necessarily by the same base.
What?
Not necessarily.
Well, not necessarily by the same base, but what if I use a different base? What's going to happen? It's going to be just changing. If I choose a different base, it's going to be the same kind of scale, except it's going to be a linear translation, right? If I, have the base of the log, the line is going to tilt, but it's still going to be a line, okay? Any questions about that? So it's important to think about why it is, but basically as a consequence of what I said, you get straight lines on log-log plots, okay? Any questions? This gives you an interesting way to think about things. If wealth is power law distributed, what do we know? When I did this, Bill Gates had a measly $80 million. He probably went up. He may have lost it when he got divorced a little bit, but whatever it is. Let's say that this was the richest person. If there is a power law, we would expect something like this. If the richest person had 80 billion, there's going to be some number of people, let's say 5, with about 40 billion. That would mean that there's about 25 people. Notice that's 5 times as many people halved it, right? Here again, 5 times as many people have it, okay? 5 times as people. Once you know the alpha, okay, what's the rate of that kind of decay? You can predict how many billions, how many people you have at every level of the wealth distribution, just given who the richest person is to start and what that alpha is. Okay? Any questions about that? Okay? I'm not going to prove to you that this is what the distribution should be, but I will tell you this is the distribution you see. Now, why is it that the richest people, why is it that Bill Gates has so much more money than you guys do? Okay? Because he has more money. That's exactly right. Okay? He started, he founded Microsoft. That was a great thing. Once he founded Microsoft, he had money to invest. He had the choice of anything he could invest in, right? What would happen if Skinner went up to Sam Altman and said, here, I've got $1,000, I want to put it in OpenAI? What would he say? You do nothing for me. Bill Gates says, I want to give you $1 billion. He'd say, sure, right? And that's the kind of process that basically happens. If money begets money, you get a power law. Any questions? Okay? And again, a lot of things in the world are power law distributed. Okay? If you take a look at earthquakes, okay? One thing you notice with earthquakes is, how do you measure the power of earthquakes? Richter scale. And what is a good scale earthquake? Okay, 3.5, you might get one of those here, right? California, go work in California. What's the big one going to be? Like an 8 or so. They measure it on an exponential scale. The probability, an 8 is 10 times more powerful than a 7. Okay? That's why we get 3.5s. What is a 1 on the Richter scale? It's probably something like flushing a toilet or something, right? Okay? But what's the situation? Is there ever going to be an 11-point earthquake? We wait long enough, there is going to be an 11-point earthquake. Is there going to be a 12-point earthquake? We wait long enough, there's going to be one. Okay? It's going to get rarer and rarer. Okay? But there is not an upper bound on this kind of thing, the way there is really in a similar distribution with with like height and normally distributed variables. How many people get killed in wars? Okay, you have a lot of wars that kill very small number of people. They maybe occur in schoolyards, okay? And you have small numbers of wars that kill millions of people. Has there been a war that killed billions of people? Will there be one? If it's power law distributed, we just haven't gotten there yet, right? And the interesting thing is that there are lots of things that score as power law distributions. Any questions about it? Okay, again, power law distributions often do break down at the end, so I do hope that, we're not going to get a war with 1 billion people.